Okay, today we'll see a few problems from exam of 2014. So, first example, we'll see question number 3 from the exam. So, in this particular question, we have been given a beam, prismatic beam of cardioid cross section, which is subjected to torque T and moment M about the x-axis. So, this is the cross section of the prismatic beam. Let's call this area A. This contour will be denoted by C. So this is Cartesian coordinate system and this is radial or polar coordinate system associated with particularly this cross section area. So now we have been given the components of stresses. So let's first write the stress components for this particular problem. So tau Rz is given by C1 r to the power minus half cos theta by 2 plus C2 sin theta. Tau theta z is given by C3r plus C2 cos theta minus C1 r to the power minus half sin theta by 2. And as this is subjected to torque as well, we have additional stress component apart. Sorry, this is subjected to moment about the x-axis. So we have additional stress component tau z, which is given by C4 times r sin theta. Now we have to make use of appropriate boundary conditions to find out these constants C1, C2, C3 and C4. So to use the boundary conditions with respect to tractions, we need to find tractions on this particular surfaces. So for finding out the tractions, we may need to find the normal to this contour and C. So the contour, the equation of the contour is given like r equals to 4 sin square theta by 2. So let's take the equation of contour to be equal to phi, which is represented by phi equals to r minus 4 sin square theta by 2, and we know the normal to the contour is given by an expression is del phi divided by mod of del phi. So now we are using polar or cylindrical coordinate system for this particular thing. So we'll find this del phi operator in polar coordinate system. So let's find the normal components for that particular contour C. So del phi in polar coordinate system is given by del phi over del r and 1 over r del phi by del theta. So now if we differentiate this particular relation for phi, we get these components to be 1 and minus 4 sin theta by 2 cos theta by 2 divided by r. Now we know on this particular contour C, r equals to 4 sin square theta by 2. So make use of this particular relation for r, then we get the expressions for these components of normal to be 1 and minus cos theta by 2 divided by sin theta by 2. Now this normal, this is not a unique norm, you can see, because we have not divided by the norm of this particular normal. So if we normalize this, after normalizing, we get this normal to be equal to sin theta by 2 and minus cos theta by 2. Obviously, we are considering the normal for this contour C, which is like we are considering a plane z equal to constants. So obviously, this is a z component of this particular normal to be equal to 0. So let's not worry about that particular thing right now. So we have got the expression for normal. Now we have to make use of certain boundary conditions. So the components of normal are represented usually by nr and n theta. So nr component is sin theta by 2 and n theta component is minus cos theta by 2. So now we make use of boundary conditions. So we know the lateral surface of this particular beam is traction free. Lateral surface is traction free. So let's first find the normal to the lateral surface. The normal is given by, again, so lateral surface is just like extension of this particular cross section in z direction. So nr and n theta components will be given by sin theta by 2 and minus cos theta by 2 respectively, and the z component will be 0. Now we use this Cauchy relation to find the traction on this lateral surface. The traction is given by tau times normal. Now, these are the only non-zero stress components in this particular problem. So we make other components to be equal to 0 and we write the stress tensor 0, 0, tau theta z, tau r z, tau theta z and tau z z also. And for simplicity, let's write now nr and theta, and this is 0 because nz is 0. You can see from here. We are calling this component as nr, this as n theta, and nz equal to be 0. So from this equation, we get the traction on the lateral surface to be equal to 0 along the radial direction, 0 along the theta direction, and in z direction we have a component tau r z nr plus tau theta z and theta. But it has to be equal to 0 as this lateral surface is traction free. So from this traction free boundary condition on the lateral surface, we have got the relation that tau r z and r plus tau theta z and theta equal to 0 on contour C. Because this lateral surface is nothing but this extension of this extrusion of this contour C in z direction. So we have got this condition from the lateral surface being traction free. So we'll make use of this particular relation to find some certain constants. So let's find this. So now we use this particular relation on contour C. So on contour C we have the relation for r to be equal to 4 sin square theta by 2 and terms in stresses involves r to the power minus half. So r to the power minus half, it will give us 1 upon sine 2 sin theta by 2. So we will make use of this particular relation for r in these expressions for stress components, and we use this particular relation obtained from traction free boundary conditions on the lateral surface. So if you put these relations for stresses into this boundary condition, we get an expression which looks like C1 cos theta by 2 minus C2 cos 3 theta by 2 minus 2C3 sin theta by 2 equals to 0. So to get this expression from these boundary conditions, we have to make use of this stress components and nr, which is equal to sin theta by 2, and theta, which is equal to minus cos theta by 2, and using certain trigonometric relations, we are able to get this particular relation now. So now, as this expression is valid for all theta, so one can in principle use the trigonometric relations to find out the relation between these constants. Otherwise, as this expression is valid for all theta, we can make certain choices of theta. So let's see. If we choose theta to be equal to 0, this will imply, so this term will go away and we get the relation between C1 and C2. So we get C1 to be equal to C2. Now, if we use this C1 equal to C2 in this particular relation and then choose theta equals to pi by 2. This expression is valid for all theta, so we are making certain choices of theta to get the relation between constants. So after using this particular theta value, we get the relation C1 equal to C2 equal to C3. So through this lateral surface being traction free, we have got the condition that C1 equals to C2 equals to C3. Now if we see the stress fields, so we are left with only two constants, let's say C1 and C4. Plus C2 and C3 are anyway equal to C1. So to find these remaining constants C1 and C4, we may need two additional boundary conditions which will come through the torque and moment M being applied about the x-axis. So let's use of these particular boundary conditions to find the remaining constants. So we know, so on this top surface, the torque T is being applied about the z-axis. So torque T on the top surface is given by integration over this particular cross-section area A of r times tau theta z dA. Now we are making use of this cylindrical coordinate system. So the area element is given by r dr d theta on this particular cross-section. and now this tau rz. So now we'll make use of this tau theta z expression from this. So this will imply, therefore we get this area integration would be in terms of r and theta. So the limits for theta would be 0 to 2 pi, and limits for r would be 0 to this r value on the contour, which is given by r equals to 4 sine square theta by 2. So the limits for the radius would be 0 to 4 sine square theta by 2. Now r. Now C3 in this particular expression for tau theta z, C3, C2 and C1 are now equal. So let's put C1 for all of them and take it outside the integration sign. So we are remaining with r from this, and remaining expression r plus cos theta minus r to the power minus half sin theta by 2, and additionally we have additional r from this area element, which will be like, and write it here, r square dr d theta. So this is expression for torque being applied about the z-axis. So we are not supposed to find this integration explicitly, but in principle we can find this value of this integration. So once we know this torque being applied, and if we find this integration value, we are able to solve for constant C1. So from this equation star, we are able to find the value of constant C1. So similarly, we will make use of another equation through the moment m being applied about the x-axis to find the remaining constant C4. So let's use that particular relation. Now similarly, this moment m is being applied about the x-axis. So now one has to be very careful with this particular expression. So this moment is being applied about the x-axis. So it is given by the integration over area y times tau z. One should not use radius here because this moment is being applied about the x-axis. So moment is given by integration over area y times tau z integration over area. So again, as we are integrating in polar or cylindrical coordinate system, again this area element is given by r dr d theta, and now for this y we have to make use of this y equals to r sin theta. Now if we make use of this particular relation, we get m equals to, again the limits for this integration would be for theta 0 to 2 pi, again for r 0 to 4 sin square theta by 2. Now r sin theta, C4 coming from this tau z expression, let's take it outside integration sign C4, one more r sin theta, so it will become r square sin square theta, and one r will come to this area element, so it will become r cube sin square theta dr d theta. Let's call this expression double star. Again, we are not supposed to find this integration value, but suppose if we know this moment being applied about the x-axis, and if we find this integration value through this equation double star, we are able to find the constant C4. So from this equation star, we are able to find constant C1. Through this equation double star, we are able to find the constant C4, and C2 and C3 are equal to C1. So by making use of these boundary conditions, we are able to find all these constants C1, C2, C3 and C4. Now the remaining part is kind of post-processing. So once we have got all these stress fields and constants, we are just left with the post-processing part. So whenever you are asked to find certain constants in this particular stress fields, you have to make use of appropriate boundary conditions, and after finding your constants, you can always put them back to your stress field and check whether your traction boundary conditions are being satisfied or not. So this way you can verify your solution if it is correct or not. If it is satisfying the traction boundary conditions, then you can surely say that your whatever solution or constants you have found are correct. So now from these relations or traction boundary conditions, we have found all these constants. The next part will find the forces, the net force along x, y and z direction on this top surface. We know this net force along x direction is given by integration of traction along x direction over area. So now as we are finding net force along x direction, it has to be traction along x direction. And similarly, we will find net force along y direction and z direction. So to find this, we have to first find Tx, Ty and Tz. Now on top surface, first of all find tractions on top surface. This normal is given by 0, 0, 1. And again, the Gaussian relation T equals to tau n will give us T, which is equal to tau Rz, tau theta z, and tau z by using Gaussian relation and this particular norm. Now we denote these components as Tr, T theta and Tz. Now these are the radial component, theta direction component and z direction component. We have to resolve them along this x axis, y axis and z axis. So we need to basically transform the traction vector from cylindrical coordinate system to Cartesian coordinate system. So let's say this is Ex, this is Ey, this is Er, this is T theta, this angle is theta, and Ez is coming out of board, and that would be same for Cartesian and cylindrical coordinate system. So for transforming a vector from polar or cylindrical coordinate system to Cartesian coordinate system, we have this transformation matrix which is given by cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. So we make use of this particular transformation matrix and we get this Tx would be Tr cos theta minus T theta sin theta. This Ty will be Tr sin theta plus T theta cos theta, and Tz will remain as it is Tz. And now on this top surface, Ti is nothing but tau Rz. T theta is tau theta z and Tz is tau zz. So we make use of these expressions to find out the net force along x, y and z direction. So let's find this. Fx would be given again this integration over area 0 to 2 pi 0 to 4 sin square theta by 2. Now we have to make use of this particular relation for Tx. Tr is nothing but tau Rz cos theta minus tau theta z sin theta, and this area element is given by r dr dθ. Again, we are not supposed to find the solution for this, but at least we should provide certain expression for finding the net force along x, y and z direction. So similarly, we can write expression for Fy by using Tr to be equal to tau Rz, T theta as tau theta z, and for force along the net force along z direction as tau zz for this Tz. So by using these particular relations, we can find the net forces acting in x, y and z direction on the top surface. So in a nutshell, this problem, we are given with the stress fields, we have to make use of certain appropriate boundary conditions to find this constant. So boundary conditions in these particular problems were like, first of all we have this traction free boundary condition on the lateral surface. From that we have got the relation between C1, C2 and C3. Then we are left with only two constants, C1 and C4, and to find those two constants we have used boundary conditions in terms of torque T being applied about the z-axis and moment M being applied about the x-axis. So once you got the constants, you can put them back, you can check whether your traction boundary conditions are satisfied or not, and after that, if we are asked for post-processing part like this particular thing, we can make use of this stress field to find the net force along x, y and z direction. Okay, so we'll move on to the next problem. Okay, so next problem is the bending by terminal load of a beam of rectangular cross section. So we have a beam of a rectangular cross section which is subjected to terminal load. This is x-axis, this y-axis. This load P is being applied to this along the x-axis to the centroid. So this is A and this is B. Now first of all, the cross section of this particular beam is symmetric about x and y axis both. So moment of inertia with respect to this xy will be 0 due to the symmetry of the cross section in x and y direction. The next thing, this load, terminal load P, is being applied to the centroid of this cross section. So we are not expecting any twisting of this cross section. So we know this angle of twist will be 0 and this load P is being applied to the centroid of the cross section. So by making use of this particular relations, first of all we will find this curvatures Kx and Ky. So Kx will be given by this Kx will be given by P upon T times Iyy, and this Ky will be given to be equal to 0. Now we have been given a stress field, so let's write the stress field first. So stress field for tau xz upon g is equal to, now we have to make use of this particular expressions which we have commented through to write this tau xz field. So let's write, so alpha is being 0, so now this is simplified like del chi over del x minus kx upon 4 3x square plus y square plus 2 new x square minus y square. And now we have to make use of this, we have to make use of this alpha equal to 0 and ky equal to 0 to find the simplified version of this test field. And tau yz upon g is given by this del chi over del y minus kx times xy upon 2 1 plus 2. So these are the expressions for tau xz and tau yz. Now this we have to make choice of this chi expression based on the problem. So we have been given with the two chi equations. So let's write first two chi functions. So I'll not write entire function. So we have certain terms in x and y plus 1 over g summation over some constants sine of some function of x and cos hyperbolic in y. The first equation is sine in x and cos hyperbolic in y, and the another expression is some terms in x and y. Series term will have some constant, and now in addition to that we have this is cos in x and sine hyperbolic in y. Now we have to make choice out of these two chi functions for our problem. Now you can see in this particular problem, this terminal load P is applied along the x-axis and through the centroid of the cross section. So for the definition of the problem for the loading condition and the geometry or the symmetry of the geometry, we comment that this tau yz should be odd in y. So this statement has come out of the loading condition and the geometry of the cross section. So this load P is applied to the centroid of the cross section and this load P is applied along the x-axis. So we expect this tau yz component that should be odd in y. Now if you look to this tau yz, so it includes the term which is a derivative of this chi function with respect to y. Now if we look at the both chi functions, the function of y is like cos hyperbolic in first and sine hyperbolic in second. Now we have to differentiate differentiate this chi function with respect to y. So if we differentiate the first chi function with respect to y, this will give us sine hyperbolic in y. And if we differentiate the second one, it will give us cos hyperbolic in y. Now we want this tau yz to be odd in y. we have got sine hyperbolic for tau yz from the first chi function and cos hyperbolic in y through the second chi function. So as this yz, tau yz component is odd in y, this is not accepted because this cos hyperbolic function is even and sine hyperbolic function is odd. So we'll definitely go with the first choice of chi function. So let's write the chi function explicitly. Now we choose the first chi function. This chi function is given by this chi is c1 x cube minus 3xy square plus c2x plus 1 over g summation a upon 2m minus 1. This is sine of 2m minus 1 pi x upon a cos hyperbolic of 2m minus 1 pi y upon a. Now we have to make use of this chi function into this stress fields to find an explicit relation for tau xz and tau y. So let's find first. So now tau xz upon g is given by, so I'll write these expressions directly. Now we have to make use of this chi functions into these particular relations to find an explicit expressions for tau xz and tau yz. So let's find. So I'll write it directly. So this would be tau xz upon g is given by c1 3x square minus 3y square plus c2 plus 1 over g summation. This includes am cos of 2m minus 1 pi x upon a times cos hyperbolic of 2m minus 1 pi y upon a minus an additional term kx upon 4 into bracket 3x square plus y square plus 2 new x square minus y square. And similarly, if we put this kind of relation into the second expression, we got a relation for tau yz on g, which is equal to minus 6c1xy plus 1 over g summation am sine of 2m minus 1 pi x upon a sine hyperbolic of 2m minus 1 pi y upon a minus an additional term we have is kx xy upon 2 1 plus 2. Now we have got, so far we have used the loading conditions, the geometry or the symmetry of the cross section to find these particular expressions. So that we have found the simplified expression for tau xz and tau yz. Then based on the geometry of the cross section and loading conditions, we have commented about tau yz, and on the basis of that we have chosen the chi function and we put this chi function to find the explicit relations for tau xz and tau yz. Now if you see these expressions for tau xz and tau yz, this involves constants like c1, c2 and am. Now we are supposed to find these constants again through certain boundary conditions. So now we make use of boundary conditions. Now we don't need this anymore. So we have expression for tau xz and tau yz. So again, this prismatic beam is subjected to terminal load. So if you see the lateral surface of the beam, it is traction beam. So do traction beam boundary conditions on lateral surface. We get two expressions. Basically tau xz at x equal to plus minus a by 2 equal to 0 and tau yz y equal to plus minus b by 2 equal to 0. Now again, one can use an expression for this Cauchy relation t equals to tau n. Suppose if you are considering this particular edge, the normal will be given by 0, 1, 0. If you are considering this particular edge, the normal will be given by 1, 0, 0. then make use of this expressions for tau xz. So basically we have non-zero compounds for spaces like tau iz, tau xz and tau zz. So use that particular relation and use this traction free boundary conditions. So by using all these things, you get these two relations. Tau xz at x equal to plus minus a by 2 would give us 0, and tau yz at y equals to plus minus b by 2 equal to 0. So what we make use of these boundary conditions to find the constants c1, c2 and am. Now you can see here, these are the two boundary conditions and we have three constants. But still we are able to find all these three constants through this boundary condition. So let's see how. So this particular boundary condition will lead us now tau xz, we have an expression, explicit expression for tau xz. So this tau xz at x equal to plus minus a by 2 equal to 0. So if we make use of this relation and put x equal to plus minus a by 2 in this particular expression, we can see this term, it will be like cos of, if you put a by 2, a gets cancelled, so it will be 2m minus 1 pi by 2. So it will be like odd multiple of pi by 2. So this will go to 0. So anyway, the series term is not contributing anyway when we are computing tau xz on x equal to plus minus a by 2. So this term is gone. So we are left with only this and the last term. So if we choose, if you see it carefully, we are putting x equal to plus minus a by 2. So the expression now through this boundary condition will involve certain constants and y square term. So we will write these constants and y square terms separately. Now we will write it separately. So it will give us 3a square by 4 c1 plus c2. We will write constant term separately minus 3 by 16 kx square minus mu by 8 kx square. These are the constant terms by putting this particular into this relation. Plus additionally we have this coefficient y square with set of constants minus 3c1 minus kx by 4 plus mu by 2 kx equal to 0. So by making use of this particular boundary condition, we have got this relation which includes constants plus y square times another constant. Now this expression is again valid for all y. So you can think like this coefficient is multiplied by 1, this coefficient is multiplied by y square. So 1 and y square kind of linearly independent functions and we are setting it to 0. So combination of this linearly independent functions is 0. So independent constant has to go to 0. Or in simple way, we can think of, let's put this, as this expression is valid for all y, let's put y equal to 0. So by putting y equal to 0, this constant goes away. So this constant will set it to 0, and once this constant is 0, we are left with only this term. Now again, this expression is valid for all y. So if you put any non-zero value of y, we must choose this constant to be equal to 0 to satisfy this equation. So in short, independently the terms in these two brackets, the constant terms in these two brackets, we are putting it equal to 0. So from these two conditions, we have got two equations in terms of C1 and C2, and this will give us the value of C1 and C2. So from this, we get this C1, which is equal to minus kx upon 12, 1 minus 2b, and C2 equals to kx a square by 4. So by using only one out of two boundary conditions, we are able to find both the constants C1 and C2. So now we are remaining with only one constant Am, and for that we have an additional condition tau yz at y equal to plus minus b by 2 to be equal to 0. So let's write this C1 equals to minus kx by 12, 1 minus 2 and C2 equals to kx a square by 4. Now we are left with only one constant and one boundary condition. So this we have used. So we are left with only this condition. So we are left with tau yz on y equal to plus minus d by 2 equal to c1. Now, again, now we know the values of constants c1 and c2. So, while using that particular boundary condition, we put y equal to plus minus d by 2 and c1 and c2 values whatever we have obtained from the previous boundary condition. So, after putting all these particular values into this relation, we get summation over m 1 to infinity pi x upon a sin hyperbolic 2n minus 1. Now we have put y equals to b by 2, so it would be 1. Now we are using y equal to b by 2. You can use y equal to minus b by 2, you will get the same expression for this, which is equal to mu times kx x times dg. So, one has to use the value of c1, value of this y equals to b by 2 into this particular relation and equate it to 0. So, we get this particular expression. Now, you can see this term is constant. The sine hyperbolic of some constant. It can be taken to other side. So, we are left with only left hand side will include a series in terms of x and right hand side will have these terms divided by this another constant. So, we can write this again, summation am sin 2m minus 1 pi x upon a leave us 1 upon sin hyperbolic 2m minus 1 y b upon 2a times mu times kx x dg. Now, to find this constant, on the left hand side we have a series and on right hand side we have certain function. So, to find this constant am, we have to make use of orthogonality conditions. So, we will make use of orthogonality of trigonometric functions here. So, what we do here, we multiply both sides by sine of 2n minus 1 pi x upon a and integrate over the domain minus a by 2 to a by 2. A by 2 to a by 2. This is series, the original series. am sin of 2m minus 1 pi x upon a multiplied by sine of 2n minus 1 pi x upon a integrated with respect to x equals to, this is constant, we can take it outside integration, so sine hyperbolic 2m minus 1 pi b upon 2a, again integration from minus a by 2 to a by 2. So basically we have multiplied both sides of this equation by sine of this particular thing and integrated over the domain minus a by 2 to a by 2. So this will have mu kxx bt dx. Now we know, so this is orthogonality relation for trigonometric functions. So if we integrate this particular thing, we can think of this is series and multiplied with certain term and integrated over minus a by 2 to a by 2. So this is non-zero when m is equal to n. So if you take this a1 plus a1, a2, a3, a4 and if you take certain value of n, this will give us only one component and that would be non-zero only if m is equal to n. So otherwise the values from the terms from this series expression including m will be not equal to n are not going to contribute anyway because this integration will be non-zero only if m is equal to n. So we make use of this particular orthogonality relation to find the constant am. So this integration, this will only give us one constant which is am. Again, you can write in terms of like delta mn times whatever because this is non-zero when m is equal to n. So at the end, you have to replace n by m. So you get an expression for am like 1 over. This integration will give you value a. So a can be taken that side. Sine hyperbolic of 2m minus 1 pi b upon 2a. Again integration we have added this k by 2 nu times kx xdg dx. Again, we are not supposed to find this integration, but we have an expression which can give us the value of Am. So basically what we did in this problem is, based on the symmetry of the cross section of the beam, we have commented certain terms like moment of inertia with respect to xy to 0. As load P is being applied to the centroid, there is no twisting of the cross section, so alpha is equal to 0. Then we have found the curvature kx ky. Then we have made use of this particular things to find out the simplified expression for tau xz and tau yz. Then we are asked to make a certain choice out of two chi functions given. So from the geometry of the symmetry of the cross section and the loading conditions, we expect this tau yz to be part in y, and on that basis we have selected the first chi function, and by using that chi function we have got an explicit expression for tau xz and tau yz. So now in these two expressions we have this constant c1, c2 and am. So to find these constants we need boundary conditions. So the boundary conditions is like, first is lateral surface is our traction free. So from traction free boundary conditions on the lateral surface, we have got these two boundary conditions, tau xz at x equal to plus minus k by 2 and tau yz at y equal to plus minus b by 2 equal to 0. So by making first condition, by making use of this first condition, we have got the relations for c1 and c2, and by using the next condition, we have got an expression for am. So for getting this expression for am, as this involves series expression, we have to make use of orthogonality of the functions to find out the constant am. So by making use of this appropriate boundary conditions, we have found the values of c1, c2 and am. So to summarize all these exercises, most of the problems you will be given with the stress fields, in which it involves certain constants. So you have to find these constants by making use of appropriate boundary conditions. To check your solution, you can always put them back to your stress field and see whether your traction boundary conditions are satisfied or not. So this way you can check your solution or verify your solution. And once you have found all these constants, the rest of the things, as we have seen in the first example, we are asked to find the forces, net forces on x, y, z direction. That would be kind of post-processing part. So the important thing is to use the boundary conditions, traction boundary conditions appropriately to find these constants. Okay, so we'll stop here.